Linda Vogel, I'm the Research Engagement Manager for the Georgia Tech Manufacturing Institute that sponsors this Lunch and Learn series. We have two more this semester on April 20th. Michael Kirka from Oak Ridge National Laboratory will be here. And on April 27th, Professor Kumar from the University of Glasgow. We hope you will join us again. I also wanted to flag that the last week of April, we're having some events around the AMPF grand reopening. So on the 29th, there is a consortium meeting and a technical symposium. And then on the 30th in the afternoon from 2 to 6 p.m., the lab will be open for tours. So you can just drop in, no need to schedule or register for that. I'm pleased today to welcome Charles Fox from SEI. He's the Senior Director of Client Development there. So Charles has a kind of non-traditional path to engineering work, which is appropriate because I feel like ESI is a non-traditional place for engineers to work.
I would agree, yeah.
So Charles began his career on the rural roads of Iowa, where early experience with his veterinarian father instilled a deep respect for community leadership and curiosity. After earning a doctorate in a biology field at Iowa State University and completing a neuroscience fellowship at University of Michigan, he made a bold pivot, leaving academia to join a team that pioneered the use of 3D animation in complex investigations. And that is a lot of what ESI does. I was fortunate to visit there, it was last summer or fall.
Yeah.
But was really fascinated by the way you all use mechanical engineering and material science and all these other components to investigate accidents, and that there's both a creative component to that work, because a lot of times what you're studying has been destroyed in the accident, but yet this high degree of accuracy that's needed because of the nature of the work. So welcome, thank you for coming.
Thank you so much, Belinda. Thrilled to be here today at Georgia Tech, because I don't know, like, I'm very proud of Iowa State University and coming from, you know, a college of science and technology, but man, Georgia Tech, like, here we are, right? This is, I constantly, you know, a kid that grew up on a farm in the Midwest, you know, getting the opportunity to go to Iowa State University is pretty cool. Getting the opportunity to be here in Atlanta at a place like this is amazing for me. So thank you so much for inviting me and having me here. How many of you are familiar with forensic engineering? Any of you kind of touched on forensic engineering? It is crazy, like Belinda said, because everything that we encounter is a one-off event. You've never seen anything like it before. Things are badly damaged, and you've got to try to determine what caused an accident. And I like to relate like a plane crash to people. A lot of times the wreckage from aviation accidents you can pour out of a bag, right? And there's lots of broken parts after a plane crashes. Determining which ones might have broken in advance of the crash is the trick to all this. So what I'm going to do is, if my slide will advance, Clicker, is there a place I need to? Maybe it's not on. I think it's just on. No. There we go. Now we're working. How many of you grew up playing in a sandbox? Right? A few, like I sure did. Like when I was 5 years old or so, my dad built a sandbox in the backyard of our house and sort of lined it with silo stays, because we lived on a farm. So that was what concrete blocks were like. It was maybe a 10 by 10 sandbox. And my friends and I would, you know, build roads and moats and redirect rivers with buckets of water. And, you know, we were like a construction, right? And then, you know, fortunately I outgrew the sandbox. There was some point where it wasn't cool anymore. And I went off to Iowa State and I thought about neuroscience for a chunk of my life. And then in about 1995, I had the opportunity to come back to Ames, Iowa and join a startup company that had a National Library of Medicine grant to reconstruct the human body in 3 dimensions. Now, it doesn't sound like a big deal now, but in 1995, that was a pretty big deal. So I decided I didn't know what I was going to do with my life. I'd been through 2 postdoctoral fellowships at the University of Michigan. I needed a job, right? And so I'm like, hey, I'll work on this grant. It's 2 years. no Ames, Iowa, easy to move back there for a couple of years and I'll figure out my life. And it became 25 years in this space. It was really interesting. So I came back to the sandbox in a sense because the sandbox was now inside of a Silicon Graphics computer. And one of the things we got really excited about in terms of investigating accidents was one of the levers we could pull was creating the space of the accident happened. And if we could recreate the space inside the computer, we could begin to ask interesting questions. And so capturing space is the first thing I want to talk about with y'all. And this will just kind of build to more detail. So in the beginning, in 1995, when we started doing this, we were out there with tape measures and things like that to define space. It was pretty crude. We had a sonic digitizer where we could digitize a vehicle. You'd maybe end up with a few hundred points if you spend an entire day digitizing a vehicle. And that was pretty amazing, again, at the time, right? But in about, commercially, laser scanners became available and, sort of ubiquitous, maybe around 2013, 14, 15 is when we started seeing laser scanning data coming into this space. And instead of having 25 measurements to this room, we had 1 million, right? We could put a laser scanner in a space, we could capture it very accurately. And there's a variety of different scanners that we use. The Faro scanner here on the left is the most common form that we use. It's kind of the one you would place if you were trying to capture a building exterior, a job site, an accident scene. And it's these capture out about 300 meters. They'll capture roughly 1 million points, millimeter accuracy, pretty good data. Not great for building interiors. Like if you wanted to capture the interior of this space, you could do it, but you'd be at it for days with one of these scanners. Instead, we would use like one of these mobile scanners. So you can actually put on your body. It has two systems on it that capture in the basically in the vertical plane and the horizontal plane. And you just walk around a building and it'll capture it fairly accurately. And then if you need really high level of detail, we have hand scanners that we can scan components like the gear on this rooftop crane was cracking. And the hand scanner will scan down to like 1,000th of an inch. So we can get really detailed features out of structures that way. The data looks something like this. You can mix and match the data. You can use the stationary scanner, the walking scanner. It's all just points. So you can align those and come up with these clouds that are this three-dimensional sandbox that I'm talking about, this 3D space. We can hang them on drones. We can put them on cars. We can get at spatial data in virtually any environment that you want spatial data from. So when an accident happens, we can characterize the scene in a high level of detail. This is an example of a large scene that we captured at a petroleum plant that had an explosion. And so we used the laser scanners to capture this space. You can see it's a fairly large area that was affected. Hundreds of scans go into a point cloud like this one. Everywhere you see one of these little dots on the ground, that's where a scanner was placed. It doesn't capture, maybe about a meter circle right under the scanner. So you rely on neighboring scans. That's why you can see that. And you can assemble a detailed structure like this, and you can go into it in virtual reality and walk around. And that's what our investigators will frequently do with the data that comes right off the scanners, is we'll jump into one of our VR labs, put on the headset and walk around the space to try to figure out what happened, right? So this is a pretty common exercise for us to do that. And it gets the investigation started. You begin to get the right questions out of the space. Almost always when one of these cases comes in our door, there's a story part already. The attorneys are saying, hey, we got this case, this happened, X, Y, Z, and we want you guys to investigate it. And then we jump into space and realize there's no way X, Y, Z happened. The space begins to constrain the story part right out of the gate. So that's where the investigation begins, is really in capturing space. An example of that in the context of a case is the case that happened. This was a case with it was a landscaping crew. They were breaking up a sidewalk at a residential space kind of back through that gap. And they were using this machine It's like a self-propelled wheelbarrow. It's called a concrete buggy. And so this machine allows you to load heavy stuff in it, like chunks of concrete when you break up a sidewalk, and haul it out to something else. And so this guy was operating this concrete buggy. They were breaking up the sidewalk. He was bringing chunks of it out. They were putting it in a skid loader and loading it into a dump truck on the site. So what happens? How do we capture this space? So the first thing we do is to go out there with our laser scanners. And the thing you need to appreciate is by the time we're involved, the accident's cleaned up. It's usually gone. It's very rare that we're on site with our scanner when the accident happened. And so we're out there a few months later and we capture this laser scan of the scene. And one of the things you can see in the laser scan is the dump truck isn't there, the skid loader isn't there, this minivan parked in that space. But not to worry, we can rebuild it. It's fine. What we need though is this three-dimensional data because we didn't know at the time that this came in where the skid loader was, where the dump truck was, exactly what was going on, but for first responder photos. So we had a handful of first responder photos were taken at the time of the accident. And what those allowed us to do was anchor components back into the scene. So we could take, for example, this photo with the skid loader. You can see the front of the skid loader here, the police vehicle and kind of the background features. And on the right side of the slash is the 3D model that has the model of the skid loader placed in the scene. Similarly, we needed the position of the dump truck because the space in which this guy was operating was critical to us. So we used a first responder photo of the dump truck. The victim was still on the ground at this point, and we're able to align that into the 3D model. Once we do, so this is kind of the technique where there's a series of points that you pick to make this alignment. You're probably all familiar with how this works. If you know the lens settings on the camera, that's helpful, but you don't have to know it to back this data out. Then we could do a couple of things. One thing we could do is do a digital simulation of what might have happened with this particular machine, right? And so that's where we start. But the other thing we could do is because we had the laser scan and we had placed models of scans of the vehicles back in the scene, we had a dimensionally accurate space, so we could reconstruct it physically in our labs. And so we did that too, where we reconstructed the tailgate, features of the tailgate of the truck. We got a concrete buggy and we could work with real surrogates with a machine to try to see how does their body interact with the machine if this happens or that happens. And what we were able to figure out was when the victim backed up the concrete buggy to the back of the truck, the geometry of the tailgate of the truck sort of pushed him over the controls and he was unable to release the controls that would have stopped the thing from backing. So this thing was sort of continuously backing into him until, some random event happened and he fell down and they were able to rescue him. But his injuries were pretty significant from that accident. So I use this as an example of, we didn't really have any motion data in this particular case. We just had three-dimensional spatial data to work with in this case. But because we had this sandbox to interact in and play with, we could start to eliminate possibilities. And so this tool really helps you carve away at what someone thinks may have happened and sort of narrow it down to it needed to be this scenario. A lot of times we convert this kind of thing into a 3D animation. And in this case, we really didn't need to. It was a pretty simple scenario. So we could work through the movements. And in this particular case, this machine was placarded for having an adequate amount of space to operate it. And they were operating in a space that was too small. One of the things I see it all the time when I'm riding around Atlanta. It's like so easy to integrate safety into something like this. Like they literally were moving the skid steer. They would load this up, move the skid steer, load the truck. They could have easily moved the skid steer a little further back, the truck a little forward. There was really no reason to operate in this constrained space, but they did. And you see this happen a lot where somebody just forces something to happen, because of the way it is, right? So anyway, interesting case. That one just really connects on space. The next one is capturing time. Well, how do we do that? Right? Well, this is oops. Hey, is there a way I can push button to make the video play? I think it's the. This is just some knucklehead cutting his grass in Grant Park. It's funny. Madeline and I were talking about. It turns out Madeline and I are neighbors. I live just down the street from her in Grant Park, and I wanted some security camera video to make the point I want to make with this. And I grabbed some things, and everything was either from a case that I can't show, or it's going to have copyright associated. But you know what? My own Ring camera footage is mine. So this is me just cutting grass in front of my house. My Ring camera capture it, and this is everywhere. You can't go anywhere in Atlanta without being on video. It's sort of frightening that that's true, but I think I saw a stat somewhere that if moving around Atlanta, every human in Atlanta is captured at least 6 times on video a day. Wow. Crazy, right? And so now what happens is we have an incident like the concrete buggy or you name it, a vehicle accident of some kind, we immediately start searching for security camera footage. You start looking at convenience stores and things in the area that would have a surveillance camera. Ring cameras commonly capture these things. You see them on the news, aviation accidents where something was captured in somebody's Ring camera. So we needed to learn how to leverage this. One of the problems with security camera footage is ones that's similar to still camera footage is it's often very highly distorted. That's one of the points I want to make with this frame. You can see, I can assure you that this pillar on my house is straight, but it sure isn't in that frame, right? Like it's really distorted, right? So you have to be able to sort of unwrap these cameras in a way that you can map it back to a 3-dimensional space that doesn't have the lens distortion in it. But tools developed around that, that's relatively easily done. So I'm going to show you an accident where we use security camera footage. I'll warn you that the security camera footage itself is a little bit graphic. A runner is going to get struck by a vehicle. She survives with injuries, but I just want you to be aware, if you don't want to see this, I'll tell you when you can look again. But this whole reconstruction started with this. And so this is a typical surveillance camera on a building. This is in kind of a little industrial park. And what you're going to see when I roll this is a runner that moves from behind these trees across and gets struck by a vehicle. The vehicle's a little cartoonish because we wanted to protect the identity of the folks that actually hit her. So there she goes. She's behind the tree. Here comes the vehicle. It hits her. Now we've got to reconstruct this accident. So if you were looking away, you can look now because all the rest of the tragedy will be animated. So first thing we did was do a 3D capture of the scene. So we went out there with our laser scanners. We 3D scanned the scene. And so here's the layout, the map of everything that happened. The security camera that we saw the video from is located on this building right here. And the trick with this one was it was looking out at the street where the accident happened, but the accident happened behind a tree. She was struck right in this area, which these dark shadows just are the kind of blind spots that were in the security camera footage. But what we learned was that there was a gym in this building that people would go out and run in the gym. And they had like this little course that they would run on the road. And they knew that they would leave the gym, and if they ran out to some landmark on the road, then they came back, that there was this crack in the pavement was like their finish line. And they would record their times for this particular route. So she had run out, she had done a 2-lap run. So she had gone out, run out, was on her way back on her last lap when she was turning to head for the finish line. So how do we reconstruct the motion, vehicle motion, the human motion? Well, again, if we map that security camera footage back to 3D space, we have the paths that the folks covered, and we can map it accurately enough that we could actually mark the positions that her feet were striking the pavement from the security camera footage on the 3D space. So we painted those on the ground. We got a human surrogate, like in the previous case, that she was about the same size as the runner in the video. And we put a suit on her that had 17 accelerometers in it. So basically every segment of her body has an accelerometer in it. So we can record her motion. And the instructions we gave her was to do her best to have her feet land on the markings on the pavement that the runner covered. So play this one for you. Here we go. This is just a video with motion capture. So that's the path that we believe the runner took. And I think the last step, you can see a light one there. That's the last step we knew from the video that she took. And some of this you can also work out from human gait and things like that as well. So we have human factors, people that contribute to including where her feet land. And then the next step, this is the data now. So you can see the data that we captured. So here is her run in just kind of this universal space. This is just the software for the human motion tools. And then the cool thing we can do is the human factor scientists can take all kinds of values out of this. So if they wanted to, we could understand the forces on any one of these 17 segments per body. And sometimes that comes into play where there's an accident and we want to know what happened to somebody, and maybe we can simulate something with the human surrogate to understand what kind of force that might be. There might be an allegation that, you know, their spine was crushed by this event, and we can reconstruct the event and say, well, it's about the force of sitting down on a chair. It's probably unlikely that their spine was crushed by that particular event. Right? So the other thing we can do, though, that's really cool from the visualization perspective is we can take this data and we can put it back into an animation. So this frame shows the security camera with a runner where she's between the trees. This is an overlay with the data from our runner that ran the course. So this is not an animated, we didn't deliberately try to animate an alignment. We just simply took the data, put it back and said, you know, this is actually pretty good. We've got really pretty good alignment with our runner. And so now this is the animated version. So here's a 3D animation of that same event. Here comes our runner. She's not going to fly through the air anymore because we don't really care what happens after the strike. We just want to know what's happened leading up to the strike. And you're like, oh, great. That isn't even as good as the security camera footage, right? Well, this one we just put up there to show, like in a trial, you want to be able to show the jurors or a fact finder that this is that with their own eyes, they can say, yeah, this looks like a good depiction of what I saw in the security camera footage, because the next step is really where it becomes valuable. We can change the point of view because we have it in 3 dimensions, right? So we can take the same animation, we can run it in 3 dimensions. Here you see the truck approaching her. The truck was actually moving a little bit to the left to get around her because she was running down the shoulder, and she makes a left turn right in front of the truck. Here's another point of view. She turns to head for the finish line, fortunately gets struck. And now here's the shot you'd really like to see, right? What's the driver of the vehicle sees? The vehicle approaches. And again, our human factors people determined that this was too short a reaction time, that by the time you could perceive her starting to turn, there was no way you could get your foot to the brake and get the vehicle stopped in time to not strike her. So we talked about space and how that influences things. We talked about time and how that helps us solve problems. In many cases where we take the laboratory out into the world and we capture space, that's enough. Like we can really come up with something that helps the legal industry understand the outcomes of this. And sometimes these go to trial. It's rare now. I think something like 4% of civil litigation goes to trial. Most of the time it settles. And usually something like this, a tool like this, helps it settle. Because when both sides can see the same thing, it changes the argument. You go from kind of random, crazy arguments about what might have happened to narrow down to it's either this or this. And often that will help drive a settlement because the sides can get to agreement around a much more narrower set of arguments. But sometimes space and time, as good a job as we can do with that, don't get you all the way there. You understand what happened, but you need to know why it happened. And that's where the laboratory really comes into play for us. That becomes an important space because we can look at parts that are broken. We can look at other evidence in ways that help us determine what might have failed. And so I think the last little bit of time here and give you a couple cases that show that. So aviation accidents are extremely interesting. I love flying. I'm actually a pilot. I'm not current anymore, but I used to fly in my younger days. The name's Iowa. And so the intricacies of flying and the skills it takes to do it is all very interesting. And the other thing I think that's really interesting about it is almost always the metallurgists tell us what happened in a plane crash. We reconstruct flight paths and we do all the things like you see on the ground with a ice cream truck or whatever. We do that, but the metallurgists often tell us the story because the question is, did something fail on the aircraft that caused this accident? And I'll tell you, in the aviation space, our organization works on both sides of the V. We represent defendants, or we don't represent anybody, actually. We work on behalf of law firms that represent defendants in cases, and we work on behalf of law firms that represent plaintiffs in cases. And I guess what I like to say is they're like, well, who likes to hire you? It's the lawyers that want to know the truth that like to hire us, because what we do is going to reveal what happened. And if it's not a good answer for them, they need to be okay with that and go resolve the matter in that way. If it's good for them, then they're going to do what they do in that space. So in aviation accidents, I think I mentioned in the abstract for this that the scientific method, like in many areas, is what really yields the truth in these cases. And so we start with a hypothesis and we try to disprove it, right? Like any other scientific experiment. The thing is, in our space, the hypotheses come to us because the plaintiffs have the hypothesis. In the aviation space, we typically work on the defense side. In fact, we really always work on the defense side. And that's because we have such a long history of working for aviation, people that manufacture components for the aviation industry, that we feel like we have trade secrets that it wouldn't be ethical for us to work on the other side of the V. We know how they do things. We know too much to really ethically represent plaintiffs in this space. So that's going to be the perspective here. And so the plaintiffs come with the hypothesis, hey, this plane crashed and your part failed, and this is what caused the accident. And so the question is, okay, well, did our part fail? Did our client's part fail in the course of this accident? I'm going to talk about two cases in this regard and how we've worked in this space. The parts on the left, these are seat pins from a Cessna 210. I'll tell you, I'm going to get into some details on that case, but that's that component. This is the interior of a turbocharger from a Beechcraft Bonanza. So the first case involves this Cessna 210, and this is a high performance aircraft. And this pilot had a lot of experience in 210s, but the 210s he had most of his experience in were like conventional, like an off-the-shelf Cessna 210, which has a 6-cylinder turbocharged reciprocating engine. He had just purchased this 210, which had been highly modified to have a turbine engine in it. So this is now essentially a turboprop 210, very, very powerful, high performance airplane. And he has a handful of hours. I don't remember off the top of my head, 20 some hours or something in this particular aircraft. He and a buddy have flown into this. This is, I believe this is Salmon, Idaho. It's a high altitude airport, which impacts the performance of airplanes. When you're high altitude, it will affect a turbine engine less, but it still affects your wings lift performance and things like that because the air is less dense. And they depart from this unimproved field. It's just essentially a grass strip on a sandbar in the mountains. So this is the reconstruction like we would do, like I showed you with the ice cream truck striking the person. In this particular case, we had ADS-B data, which is essentially a form of GPS data that gives us fairly reliable points. We also had done a number of test flights from this field. So we had data from a similar 210 in this configuration. They depart the field a little early, a little too steep. The plane's kind of on the edge of a stall all the way out on their departure. They don't end up achieving flight and the plane crashes. It probably would have been okay having bellied it on the other side of this creek, but they hit this little swale, it flipped over. It was not full of fuel. They had to be light enough they could fly to a larger airport to get fuel, but there was enough fuel that it was a post-crash fire and destroyed the airplane. Both of the occupants were killed in this accident. The allegation in this case by the plaintiffs was that this is a seat slip case. So Cessna aircraft have this system where the seats roll forward and back on aluminum tracks that have holes drilled in the aluminum, and there are steel pins that go up and down that drop into the holes that keep the seat in position. There have been a history of cases in different models of Cessna aircraft where the pins are not seated in a hole in the track. And so when the airplane takes off and changes the angle, the seat slips back. Reflexively, the pilot grabs the controls and over rotates the airplane and it stalls and crashes. And so there's been a history of these. And the question was, did that happen in this particular accident? So we did the space thing, we did the time thing. Now we needed to do the lab thing. So we're going to do a little bit of a combination of the two here. This is our 210. And what we could do, since we had the movements of the airplane by reconstructing its motion, we had forces that were happening on the occupants of that airplane. And so this animation is going to summarize that. These are two occupants. We use a tool called Matimo, which is a mathematical simulator for crash test dummies. It closely approximates the movements of people in this. And so imagine, we're moving down the runway. They take off, they impact the ground here. We've got their movements simulated here, and it simulates the forces. And what it would do is we would expect the pins to have bent based upon those forces. And sure enough, the pins recovered from the fire were bent. And so what that told us was the seats did not slip in this aircraft. The pins were in position. Unfortunately, in accidents where there's fires like this, the tracks are aluminum and they're often lost in a post-crash fire. So we didn't have the tracks themselves, but the fact that the pins were bent, both actually for the pilot side and the passenger side, indicated that the seats were in place. In this particular aircraft, it wasn't the greatest hypothesis anyway, because Cessna had come up with some aftermarket stops that you install on the floor of the plane to avoid the seat slip issue, and they were in this particular aircraft. So we felt pretty comfortable that wasn't what happened. And what did happen in this case, you would think our job is done here, but you often need to offer an alternative explanation. Well, what did happen? Well, turns out what did happen were these guys had gone to Salmon, Idaho to go elk hunting, and they were successful. They actually managed to shoot an elk, and they had 800 pounds of elk in the backseat of that airplane. And so that plane was heavy, trying to get off a high altitude airport. We actually had a test pilot that was able to fly a similarly configured aircraft off that field, but it was like you had to really know that airplane. It just fly it perfectly to get off that field and go up the river. So we did an animation of what an actual departure would have looked like. And then we did another animation that showed what it would look like if you were unloaded, and that plane leaps off the ground, unloaded. So it was unfortunately an inexperienced pilot in an aircraft that he thought he knew the performance of, and they managed to exceed its ability to get out of there. Probably my favorite airplane. Absolutely love Beechcraft Bonanza. It's such a cool aircraft. But we've done a number of crashes with them. And in this particular crash, it was a Bonanza that a pilot was doing recurrent training in. So there was a pilot and an instructor in this particular aircraft in California. They were doing touch and goes at an airport, and on the last departure before the crash, someone on the ground witnessed the plane smoking, that there was smoke coming out of the exhaust on the aircraft. The plane failed to climb out and actually struck the roof of, I think it was like a movie theater. It was a building, struck the roof of the building, and then came to rest on the ground. And the allegation in this particular case, or the hypothesis for us, was that the turbocharger had failed in this aircraft. And so with the turbocharger failed, you had less air going into the engine. So it would have been too rich on that departure without a turbocharger, which would have explained the smoke, and it wouldn't have enough power to climb out normally without the turbocharger. And so that led to the crash. So that was our hypothesis in this case. So we were working for a legal firm that was representing the turbocharger manufacturer. If you're unfamiliar with a turbocharger, it's not like a turbine like the previous airplane. A turbocharger actually takes in atmospheric air. So cool air from the atmosphere comes into the turbocharger and is propelled into the engine at some desired pressure. So you're going to create high pressure air on the intake of the engine. And what drives the impeller on the turbocharger is exhaust gas. So you have an impeller and the exhaust flow that is driving the intake air on the turbocharger. So this thing spins at fairly high RPM. It has to be cooled. A lot of it is cooled by oil that's pumped through it. And there was an allegation that the oil was not being pumped through it properly. They saw coking on the shaft and the bearings in the turbocharger, which is actually quite normal. It operates at high temperature, but the allegation was, look, this thing has failed, and that's what caused the crash. So our team did what you would anticipate. We did the space and the time, and then we did a metallurgical analysis. So this is our turbocharger. And this is going to be during the animation of the accident sequence. So imagine the accident sequence happening. First impact offsets the wheel. This wheel causes some rotational scoring on the interior of the housing of the turbocharger. On the second impact, when the plane hits the ground and comes to rest, it seizes the turbocharger. How do we know this? Because these events leave a mark. And so we can actually look at the inside. Now, this is the housing of the turbocharger. And you can see these marks. The air would normally be flowing from behind the screen through this Addison going through the impeller. You can see these marks on the inside of the housing that would not normally be there. And if you really carefully look at these marks, you see there's actually two sets of them. There are witness marks from the first impact that are not evenly spread around the housing, which is probably asymmetric forces, like it didn't hit the theater in a head-on kind of fashion. And so we have these marks on one side where the impeller impacted the housing. And then we know it kept running because we have this rotational scoring going on. So we know that the impeller was spinning. It wasn't stationary at the time of the first impact because we have this rotational scoring going on. And then we know it was spinning until the second impact because now we have the second impact witness marks where it jammed the impeller into the housing. So that impact was forceful enough that it actually stopped the impeller from spinning And you can see that where it dug in around the housing of the turbocharger. So this little animation just shows the impeller itself. You can see the part of the housing where the bearing lives for this is cracked. That's an impact fracture. Oops. Play it here. And like the seat rails, we often compare our 3D data back to photographs that we take in the lab. So now here you can see the distorted blades on the impeller from striking the inside of the housing. So in these cases, this is really helpful. I will say the aviation folks keep us busy because we often go from one hypothesis to the next. Like, oh, it wasn't the turbocharger, it was some other component that must have failed. And then it all starts all over again, right? So to kind of summarize, leave a little time for some questions here. Step one is always capturing the scene. How do we get the 3D space in which this event happened? Sometimes that's adequate. Sometimes 3D space reveals enough about what happened that we can give a satisfying answer to an event, but sometimes it's not. So the next step is then reconstructing the event. In the old days, that used to be an expert's opinion, right? Well, you know, to leave these tire marks, it must have been going this speed and to do this. And we would animate that opinion just to help the fact finders understand what happened. That still has value. There's always some place that there's a gap that we need to fill in where somebody doing some math and figuring it out is really important. But a lot of times we can get video. I showed you some Matimo simulation where you use simulation to get that data. We can use that approach to understand what happened over time during an event. When those things aren't enough, though, the next step is to move into the laboratory. And that's where the metallurgists can also store the materials people, you know, some kind of testing we can do in the lab where we can drop test something and figure out what the marks look like when you do that. So, as Belinda mentioned, it's a crazy lab because it's not like we do the same thing all the time. We do some standardized testing, but for the most part, it's figuring out how you're going to rip a helmet apart or how you're going to reconstruct something that happened in a way that we can create a similar pattern of evidence to the material that we have from the scene. And then I think it's always important at the end of the day to integrate all this back together in a way that you can tell the story. The fact finders are usually not engineers. They might not have a scientific background. If they're a juror, you need to be able to explain this in a way that really helps these events be clear. And so it's a fascinating space to be in. Love to take any questions you have after all that. Yeah.
Thank you.
Oh,
Is there any background required to be in these fields?
yeah, so most of it's highly variable. As Belinda mentioned, I'm a neuroscientist. So I don't, when I did consulting, most of my work was in the biotech space, helping companies understand their intellectual property and how they might use that. If it's aviation space, we have people with just unbelievable experience. So the senior people, you know, most of them have PhDs in aerospace engineering. Some of them have military flying experience. We actually, for a while, I don't think he's on our staff anymore. We had an astronaut on the staff. Hoot Gibson had landed the space shuttle 4 times. So it's pretty hard to argue with a guy who landed the space shuttle that he didn't know how the plane flew, right? And he did test piloting for us. So sometimes we'll test pilot scenarios like that 210 getting out of Salmon, Idaho. So the senior people have, you know, really, you know, incredible resumes. That said, there's people that are right out of school that are interested in this field that come into our environment and come up on those teams, right? So some of the folks that I work with there now, like, you know, they came in someone maybe they freshly got their PhD in mechanical engineering, and this is something that fascinated them. And they started working with one of these investigators, and now, they're the senior investigators. It doesn't require a PhD. Some of the fields, a PhD is sort of the ticket for entry, but that's not true for all fields. We have folks with bachelor's degrees in engineering. And I will tell you, in some cases, like, one of the things that's really good to know is what people do in their spare time at our company, because you never know, you might need an expert in skateboard wheels. And, nobody's formally got that, but there may be somebody on our team that, does, I don't know, upside down skateboard racing every weekend. And they know everything there is to know about, skateboard wheels. And so they can actually help us, solve those problems. So sometimes it's formal, like it's like this kind of formal resume. And sometimes it's really informal. As you can imagine, our engineers do crazy cool things on the weekends. Some of them race, vehicles. And one of them flies warbirds at air shows, things like that. Does that help?
Yeah.
Yes,
Thank you for the presentation.
absolutely.
I'm really curious on the case that you have shown about the girl who got hit by the truck.
Mhm.
So what was the allegation, or like who made the allegation in that particular scenario?
Yeah, so in that case, she made the allegation that the driver of the truck was negligent in striking her. And so in that particular case, we were working on behalf of the company that owned the vehicle. They had some responsibility in, their driver's behavior. That happens frequently. And so what we were trying to determine for them is, because honestly, they often come to us with, look, we're a company, our drivers, they might have been, who knows what they're doing. They might have been looking at their cell phone at the time and just ran this person over. We want to know. And so in that particular case, we were working for the company that had that operator. And in that case, that particular case settled as they almost always do. So when cases settle, there's no clear winner or loser. They paid some. And we're never privileged to what that is. They just let us know that it's settled, and that's private. But they managed to resolve it one way or another. Yes. Hey, good to see you.
Thanks, this week we talk. One thing it makes me think about is like different types of problem solving that different types of engineering roles have, and like compared to more academic research, exploratory, kind of how you kind of go about discovering things, versus like a product development where you're kind of co-optimizing factors. One thing that strikes me about this is that it seems like there's a lot of things, there's a lot of cool tools, and there's a lot of cool things that you could do to create information about a case.
Yeah.
How much, which may or may not be productive, how much, like, the word that comes to mind is storyboarding.
Yeah.
Like how much
Yeah.
kind of like weaving out of like, here are the dots that we can connect that will drive us to something that's actionable.
That is so on point, because I think you can understand that there's an economy that we operate in. So, a client's gonna have to spend money to figure this out, and they obviously want you to be efficient as you possibly can. And so there's an element, I kind of harken back to some of those senior consultants. There's an intuition element to this, that they have seen so many Beechcraft bonanzas hit the ground that they know where to start looking. It's like they can hear the fact pattern. Hey, this happened, that happened, ask a few questions, and they don't necessarily know the answer. But this is where we should start.
Yeah.
This is likely to have been the scenario. That gets at some of the proprietary things I think we know from certain manufacturers that would make it unethical for us to work opposed to them. But it's also really helpful because we can move to something that might be really likely out of the gate. The frustrating part, I think, that happens that's overlaid on top of this is you have an opposing side that's going to make an allegation, and it may make sense or it may not. It may be the goofiest thing you've ever heard in your life, but you've got to deal with it because they're going to bring that forward. And you have to deal with that. So yeah, I would say there's sort of these two competing elements where you're working on these hypotheses that you're given. You didn't, if you were authoring the hypothesis, you come up with a better one. So you deal with that one in sort of the, how do we help negate that? How do we put that one away? And then how do we show what we think happened in a way that's helpful, right? And it can be helpful in two ways. It can be helpful in the client's like, oh man, I didn't want to hear that. Well, sorry, that's the reality. We do think your part failed. We think it failed right here. We think, this, that, and that's that. Or it's like, no, this is actually really helpful for us. This is, either moves the investigation to a component that's not ours and we're out of it, or it moves the case toward some kind of dismissal, settlement, whatever to resolve.
And is there often like kind of a conversation between that expert perspective of like, this is the kind of thing that might have gone wrong, and the kind of experimentalist who's like, well, here's what I am capable of measuring.
Yeah.
Like.
Yeah. Yep, absolutely. I think everything we do, even from the level of like the laser scanning and different tools we use, there's a confidence interval that we can put on that, right? And say, hey, when we try to align this video with this laser scan, there was a case that involved, it was a Bonanza that was departing an airport in Washington State. And it was another short field, unimproved runway. They'd been there fishing. And one of the people that did not get on the plane shot video with the cell phone of the takeoff. And the plane was coming from kind of the distance toward you down the runway. And at some point, the pilot he decided not to take off and tried to stop, and it couldn't stop, and it hit a berm at the end of the runway. And what we were trying to determine was the airplane performing normally? And that's why he rejected the takeoff. Or was there something going wrong with the engine on this airplane and he rejected the takeoff because of some kind of failure? And so what we did was map the speed of the aircraft, so we could tell how its acceleration was and all. But the farther away it was in the video, the less confidence we had about the position of the aircraft, because it's just a little dot in the frame of the video. And so, we could be off by a few feet at the beginning, but as it got closer and closer, we were pretty confident in it. And so those are the kind of things we communicate, like at this point, we're this confident, at this point, we're this confident. But it was interesting. We had another case, it was an aviation case that you've probably seen video of. It was happened in Addison, Texas. There was a King Air, twin engine airplane that took off, didn't attain very much, a few hundred feet in altitude, rolled over on its back and crashed into a hangar on the airport, killed everybody on board. And it was some of the Walmart family members. So it was a extraordinarily expensive loss. And we because the plane crashed so quickly, we didn't have a lot of data, a lot of ADS-B data, we had 4 points, I think. But we had 4 security camera videos of it. And our team aligned it with a security camera video, gave a speed back to our investigator. And he's like, no. I didn't want you to give me the ADS-B data back. I wanted you to, like, we didn't have the ADS-B data. That's the speed we got from reconstructing it video. So it can be like really, really. And in that particular case, the speed of the airplane told him everything about what went wrong during the takeoff. Yes.
You said your background's in neuroscience.
Mm-hmm. Yeah.
What is the impact on the overall? You evaluate the behavior of the individual during that time frame, underpinning with all the empirical data you're talking about now.
Yeah. So we have humans. So we have human factors people that do that. I'm not part of that analysis. I did my background was much more molecular biology in the neuroscience space, and nobody's ever asked me to do anything like that. When I joined ESI and got into this engineering space, I stepped into much more of a business development role in the organization. But we do have humans factors people that testify in this space about how someone would have reacted, what their reaction times would be, in addition to like the physical stresses or what someone might be capable of.
What's the mindset of the individual driver or the individual pilot going on too?
Yeah, so oftentimes that, when we're doing that, that then involves like a toxicology analysis. So for example, in commercial trucking cases, we'll have cases where like a truck will run into a bunch of cars that are stopped on a freeway. And the question is, what was the driver thinking? And that's super hard to know and would never stand up in a court to suggest something like that. But a toxicology exam will tell us a lot of things about the mental state of that driver, not just looking for, illegal drugs, but looking for like, oh, this person has this in their blood. They probably have sleep apnea. So this might be a driver who was driving, and was dozing off, when they're driving, because the only reason you would have this in your blood is you have this particular condition. So it usually looks more like that, where we have evidence that we can tie to something.
And in trucking right now, we have all the issues of, native speaking English.
Yeah.
We have a lot of foreign speakers who can't speak the language and
Yep.
causing accidents.
And that comes into question in the warning labels. So that's a big factor in warnings labels. If you look, I noticed it the other day, I was at Lowe's looking for a ladder, and a lot of the warning labels are now pictorial because it gets you away from being tied to English.
Now, on the accident where the young lady unfortunately got hit.
Yeah.
First thing I thought of was she may have had ear pods in.
She did. She had earbuds in, and she was, thinking about her finishing time, right? And so unfortunately, she just didn't, it was just one of these little van type trucks. It wouldn't have been real noisy or anything. And yeah, we see that, we've seen people hit by trains. That same kind of thing, they're just distracted, maybe looking at their phone, listening to music. That's a big issue. Yes.
Just have a case question. When you prove that that metal for the slip of the seat was in,
Mhm.
but can it be possible that it slips and went to another housing, and in the moment of the crash, it bended?
If it did, it would likely be bent in the other direction.
So
So if the
it
seat was going backward and the pin
went in,
caught it, it would probably bend back.
but when it crashed, so it goes in, but the forces when takeoff is not that high to bend that much. But when it crashed, it bent.
Mm-hmm.
So I think the metal being bent doesn't prove that it didn't slip in my mind.
So it doesn't, so I would say in most cases we work on, you're not satisfied to 100% with any particular element. But when you combine that with 800 pounds of elk in the back seat, you start to get, what's more likely?
Okay.
And so I would say in our space, just like any other scientific discipline, nobody's going to testify that they're 100% certain that this happened. What we would say is the evidence we can collect and put together, this is probably the most likely scenario.
So-
And then a jury or somebody decides, right, what the outcome.
So you proved that that rod was in the housing and at the moment of the crash.
It was in the house. It was certainly in a notch at the moment of the crash.
And then that case was settled, or
That case settled.
so you are creating the probability to, if you want to settle, increase your chance of having a better settle.
Exactly. That's usually what's happening if you're moving the money dial, some amount, like, let's say this particular loss, they're 25 million, we're looking for $25 million in this loss, and maybe it settles for 2.5, right, after you present this. So that's a lot of what's happening behind the scenes in this legally, is just kind of moving the stakes. There are very few absolutes in this.
So I guess the lawyers are sort of your customer, or the client who hires the lawyer, then they may find you to help them with their case.
That's right. That's right. So I think it's roughly, it's more than half of our work comes through law firms themselves. So firms that use us when they see these kind of cases. We also have corporate clients that we work with that have worked with us over and over again. And they're like, hey, we want to engage you because we think if you work for us more directly, you'll understand the pattern of we want you to know our products and how they work and all those things. And it kind of takes us to another level with them. So there are some companies, it's a pretty good list of companies that we have relationships where they essentially tell their outside counsel, hey, you're going to work with ESI on this case. and they make that choice. There's then insurance companies that engage us. So a significant part of our work comes from claims people inside of insurance companies. And then there's a portion of our work, a small portion of our work that we're trying to grow that is non-litigation. So it's just helping manufacturers develop better product, have access maybe to labs and things they wouldn't normally, that kind of thing where we can help. We run into it mostly like in a recall space where you see a manufacturer contemplating a recall, and that's close to what we're seeing here, evaluating, hey, should we recall our product? What should we do to it if we recall it?
You had a lot of cases with aerospace and automotive.
Yeah.
Seem like you have a big reputation in those
Yeah.
areas, but are there other industries that or other fields that you work on?
Yeah, so aerospace is probably our, the longest history. The founders of the company, worked in that space for the most part. Automotive is big. We're moving in the automotive space, the big targets, ADAS systems and automation in vehicles. And so the landscape of litigation is changing because of ADAS. And so, we're building expertise in that space to tackle those more aggressively. We have a biomedical engineering group that is, Emily, they've been on board, is it 2 or 3 years now?
About 3 years, yeah. It's
Yeah.
Pharmaceutical, med device, med tech, biotechnology.
And so that expert came to us, he had a long history working inside those biotech firms, developing tools. And so now we've got this capability. We're building a team around him to do both litigation-based work and, what we call industrial work, which industrial to us means everything that isn't litigation-related work, right? So that's a big one for us. Another new space that we're in is called we refer to it, and I think the world kind of refers as resilient risk. So it's like climate change is having an impact. We can predict, for a lot of municipalities and various places that there are going to be really significant impacts. What can we do to mitigate that risk with engineering, not just with insurance and money and how's that going to do, but what kind of engineered solutions can we do to help mitigate the effects of climate change? So that group is really interesting. Excited to see what happens with them. We have a pretty big civil structural group that evaluates structures and damage to structures. They're always really busy after a hurricane. They all get hey, yay, we get to go to Florida. The bad news is you're gonna be at where the epicenter for a hurricane hits, so your credit cards aren't gonna work, you're gonna have a hard time finding food, but hey, have fun. Yeah, so we really do kind of cover the waterfront of at least engineering related issues.
Yeah, how is AI impacting all this?
Whew, wow, that's a whole nother seminar.
That's
Yeah, it's crazy, right? So AI is having, I think, a significant impact on this. I think there are many things behind the scenes where AI can speed us up. That said, you have to be able to have absolute confidence in any of the data that you're putting together, these things. And so whether like in some case, there are some times it really, really helps. And I would say those times are like, hey, I need a Python script to take this data and transform it in a way that I can do this with it. But I've got to be able to back check that, because if I don't know that it's doing exactly what I expect it to do, I just can't do that. And so sometimes it helps. And sometimes it's like, oh my God, this is making it so much harder because now I don't know what this data is and I've got to troubleshoot this whole thing. On the legal side, some of my attorney friends I've talked to, I had an attorney friend I was just talking to a couple of weeks ago. She got a motion for the court from the other side that was citing courts that didn't even exist. It cited like the 13th Circuit, which doesn't exist. It cited, and then she started digging into it and it was citing cases that were just hallucinated.
Yeah, that was Morgan and Morgan. They tried to do that.
It's crazy, right? So
They got busted for that.
yeah, so what she did is she called this attorney and said, hey, like I suggest you withdraw this And I won't say anything about what I think I'm seeing here, but I would suggest you withdraw this from the court. If you don't, I'm gonna call this out. And so in this particular case, he withdrew the motion and, but there are plenty of folks playing fast and loose with it, I think, that,
That's what they were doing. They had AI go out there and file all the cases down in Florida. And Florida just basically just shut them down.
yeah, and I would hate to see like it be too one way or the other, right? Like, hey, this is gonna be a useful tool in a variety of different ways if we use it responsibly. But like a lot of things, we can't have nice things because some ding dong does something and then the whole thing gets turned off, right? So I don't know what'll happen, but it's having a big impact now.
Are you gearing up to do investigations around AI?
There will be, right? I think, I was talking to, there was a case, you may have seen this one, this was a couple years ago. There was a case where it was a road rage case where one guy had murdered another guy in road rage. And in the witness statement, after he was found guilty and all this, there's this statement the family gets to make at the sentencing. And they had created an AI version of the guy that was killed, and he gave a witness statement. And it's this thing where he says, gosh, I probably in another circumstance, this guy would have been my friend, but I hate what happened and blah, blah, blah. And he makes this statement to the court as one of and it was 2 years ago, so it wasn't even that great of AI, but it was okay. And the judge loved it. The judge was like, oh, this is huge. Like, I really feel like, and so then they sentenced this guy. Does he have a right to appeal this? I would sure think so.
I would think so.
And so I wonder, I think about the Innocence Project and how they're using DNA evidence to overturn, people that have been sitting in prison for 20 years on on murder charges. I wonder if there will be something similar in the backlash from how AI is being used in the court systems now, where it'll be grounds for reviewing a bunch of these cases.
Because I can't imagine you could use it in the case itself. Like it would be like hearsay, right?
You would think.
Because
But
it's after the fact, someone is programming this person.
right.
Yeah,
Right.
that seems very
It
slippery.
seems really suspect. I would think most courts would never have allowed it, but there are a number of scary things on the legal side, I think, from a Georgia Tech perspective, from our company's perspective. If, I don't know if you're aware of this, but a court has ruled that if you put information into a public AI, you've published it and you've lost your attorney-client privilege.
Oh, wow.
And so the concern is that, let's say I'm an attorney, I go to a company to, I come to Georgia Tech because I'm going to depose someone at Georgia Tech as a representative of Georgia Tech on some litigation. And I depose them and they get a little nervous about some questions they answered that day. So that night they go home and they pop up ChatGPT and they check their answers. Well, they just published it. And they completely, on Georgia Tech's behalf, gave up lawyer-client privilege on that. And so people could completely be unaware of damaging things they could be doing, with the technology. I find that kind of fascinating, and it's gonna take a few years for that to sort itself out in courts, I think.
Well, thank you. It's
Yes,
great.
you're welcome. Thank you so much for the opportunity.